Okay, everyone. So we have another probability problem. This was involved with geometry as well. So we have a dartboard shape like isosceles trapezoid, and we are trying to find the probability that the dart is closer to the 24 inches side than the other three sides. Okay, so let's kind of see the, the figure. So we have isosceles trapezoid. So I'm going to make it a bit bigger. So let's say this is the smaller base, and then this is a side, and this is another side. So if I connect these, so this looks like isosceles, right? So this is 12, and this is 12, and this is also 12. So this part is 24, okay? So the probability that we are gonna like draw a dart that will be landing in any spot in this region, and then we want to find the probability that is closer to this 24 side inches, right? So the first things we kind of need to remember, whenever you have a like angle bisectors, so maybe it's good to remind. So let's say we have angle, right? So if you divide this angle into two equal pieces by another ray, which is, let's say, this guy. So the angle right here and right here is equal, and now we call this segment or this line is angle bisector. Why this is important? Because when you have a angle bisector, so, and then if you take any point on the angle bisector, right? Let's say this point, and drop the altitude from that point to the each ray outside of that angle bisector, right? So if you do this, these two distances are equal to each other. This is one of the most fundamental features of the angle bisector. We can prove this by a congruent triangle, but I'm not going to dive into. So I just want to remind this now, because if you take any points, regardless of like distance from the vertex, if you take this point and drop the altitude, those distances will be equal as well. So why this is important for our problem? Because we want to find where this is going to be actually right in the middle, right? So like if I want to choose a point right here, is it going to be closer to this side or closer to this side? So how do I kind of find it right in the middle? So this is where we are going to use the angle bisector. So to determine them, we need to draw a angle bisector for this angle, because anything on this line will be equal distance from the maybe this side and this side. Maybe I should label those as well to make it a bit obvious. So A, B, C, and D. So, but the question that we have to ask as well, like when you draw this angle bisector, where this is gonna actually touch on this side BC, is this gonna be like this, or this gonna be like that, or this, maybe just passing through this at C, right? So it's kind of nicer because this is gonna actually pass through this point C, because since we are trying to draw a angle bisector, which has to be, these angles has to be equal. And now this is isosceles trapezoid, which means the BC and AD are parallel. So then if this angle is the same as this one, because of the parallel line, so then these two has to be equal side, which is isosceles triangles. Since we already told this is 12, this is 12, then only way that will happen if this angle bisector goes through this actual point C, okay? So which is nicer. So that is one thing we have. And the second, if I kind of do the same thing with this, that will be passing through B as well. So that is nicer to see. And the next thing we need to say, like anything you choose like above this AC, it will be closer to AB than AD. And if I choose anything above this BD, that will be any point above that BD will be closer to BCD than AD. So, but at the same time, we have to make sure that that is also closer to AD than BC. Okay, this is not right in the middle. We have to find the right in the middle of BC and AD, because we are going to find the region that is closer to the side AD. So which is kind of the mid segments of our trapezoid. So I'm going to draw mid segment, right? So let's do that. If I draw this mid segment from the midpoint, right? So that means this guy, maybe I should label those as well. So let's say this is K for this intersection, and then this is, let's say, L. So the KL, and I'm going to call this is X, and this is Y. KL is parallel to AD. And then the BK and KA are equal because we're trying to draw a mid-segment, so we can kind of see it right in the middle. And the region we are trying to find is this piece. So this is what we are trying to find out of the whole area of the trapezoid. And the rest is just a bit geometry. So we are going to use. So the first thing we kind of want to see, you know, since we have BC and AB are parallel, then we do know BC and let's say this is T, BCT is similar to DA's T. So because the angle right here is the same as this one same as this one, we have vertical angles. And the ratio is 12/24, which is 1/2, which means if I want to say the ratio of BT over TD, so this has to be 1/2. But I don't want to just write 1x and 2x or 1k, 2k ratio immediately, because I also know like the AX or BT, like BY, I would say BY and YD is equal. So I'm going to say BY over YD is equal to each other because this KL was the mid segment, that is the line we draw, right? So now, which means BD is actually a multiple of 2 as well as a multiple of 3 because BT and TD ratio is 1/2. If I say this is 1K, TD will be 2K. And also BY and YD are equal. So if I call BY as maybe K or T, then YD also T. So which is why BD or HC, similar reasoning, has to be multiple of 2 and multiple of 3, which is I'm going to choose as 6 to be integer, okay, to make it integer. So if I say BT as, let's say, 2K, so since we know the ratio of BT to TY is 1:2, TD has to be 4D, the BD will be 6, so right in the middle is 3, so YD will be 3K, and then TY has to be 1K, so to make that integer nicer. So like you can use the same reason, TC divided by TA is also 1/2, CX divided by XA is also 1/1, and you can just use the same ratio. So now we have this triangle right here, TXY and TAD, they are also similar, and the ratio of the similarity is 1/4 because TY, okay, over TD is equal to 1/4. So if you square this guy, we got the 1/16, which is area ratio, meaning that if I name this is as A for this region, the area of the TAD has to be 16A, because when you have two similar figures, their ratio of the similarity is the square root of the areas, or square of the ratio of the similarity is equal to area ratios. So that means the whole thing is 16A, so the bottom part should be 15A. Okay, so this is something nicer. And also, we know that like the ATD is a triangle which has an area of 16A, and the base of that I would consider as TD, which is 4K, and ATB has also same vertex A, and then the base of that triangle is 2K, which is half of this one. So for that reason, I can say the area of ABT as just half of the 16A, which is 8A. So this is one of the easiest way to kind of find this area. So this is 8A. Now we have ABD as 24A because 8 plus 16. So that has a like same height as BCD, and the BCD has a base of 12, and AD has a base of like 24. So which is 1:2 ratio. So this means this guy has 24A, then BCD has to have right half of that, which is 12. So the area of BCD, okay, should be half of the ABD, which is just 12A. So in total, we have 12 plus 24, which is 36A, right? So 36A. Since we don't really need actual values of the areas, since we are looking for the ratio anyway, so which is why it's kind of easier to use the area approach instead of finding those areas separately. And what we want was the 15A as our desired region. So if you divide by 3, so that should give us 5/12. So this was a number 29, which is actually not too challenging as long as you understand what's going on. So that is why I kind of want to remind a couple of things after this problem. So we do use area approach a lot. So in this case, I use those like a 15A and stuff. This is a really powerful tool. And the similarity is always one of our a must actually. And I seen another question like this, which is what I'm going to show you real quick as well, just to see how these questions are actually similar to each other. And this is another question which using the same idea. This was actually given in 2009 in Cayley contest, which is a grade level 10 and below in Canada. So it's kind of AMC 10 level problems. So this was number 24 on that test, which is, the second from the last question, which meant to be challenging. But the problem that we just did was 29 out of 30 problems in the MATHCOUNTS state level. So which means the MATHCOUNTS kind of have same difficulty as AMC 10 or Cayley contest. So that was kind of interesting to see. Okay, anyway, I'll see you in the next video.